Hi everybody, and welcome to example 6 on page 71. This exercise is going to be similar in spirit to example 5. We're trying to come up with a formula for a linear operator that they're describing to us in words. So if we read this together, they'd like us to let t be the linear operator in R2 that projects every point in the plane onto the line y equals negative 1/3 x. Okay, and so that line is the dotted line that you see in the picture here. Okay, negative 1/3 x, just for reference. And as we did in example 5, let's, before we dive into the problem, see if we can understand what this operator is doing. Okay, so you can kind of think of it this way. If you start with a vector v, okay, like the one that they give us in a picture here, projecting means that what we're going to do is we're going to shine a light on this vector in a direction that's perpendicular to our line that we're given, and the output of the transformation should be the shadow of the vector on the line. Okay, so imagine shining that light down, and the shadow of this vector v is going to be right here, okay, because the light's going to kind of go like this on us. Okay, so you can see the v and the t of v for the particular v that they gave us in the picture. And you can imagine doing that for every vector v in the xy plane. Okay, so we're going to start this process by choosing a basis, this time beta prime equals 1, 3, and negative 3, 1. And the purpose for those vectors is, again, we're hoping that determining the value of, or the vector that we get out, that we get projected, is going to be easy to determine based on the geometry here. Okay, so to calculate the matrix of t relative to beta prime, we need to think about what would happen if we plug in our two basis vectors, 1, 3, and negative 3, 1. Okay, so let's go to our picture and see if we can reason out what the output value should be. So 1, 3, that vector is sitting right here. Okay, let me just clear a little bit of clutter away here. And what's special about that vector is that it's perpendicular to our line. So the question you want to ask yourself is, if you shine the light perpendicular to the line, what would the shadow of that vector look like? Well, because it's perpendicular to our line, the shadow is just going to be a single point. It's going to collapse down into the origin. And what that means then is that t of 1, 3 is 0, 0. And 0, 0 is an easy number to write as a linear combination of our basis vectors. It just looks like this. Both zeros. Okay, and then we come to the second one, t of negative 3, 1. Negative 3, 1 is right here. And notice that that vector is directly on the line that we're projecting onto. So what would its shadow be? Well, it's going to be the vector itself because it's already on the axis of projection that we have. So t of negative 3, 1 is just going to be itself. Okay, and then the question is, how do we write that as a linear combination of 1, 3 and negative 3, 1? Well, conveniently, negative 3, 1 is one of the two vectors on our list, so we just need to put a 1 in front of that and a 0 in front of the first thing. Okay, and therefore, our matrix is going to be, let's see, 0, 0 for the first column, and then 0, 1 for the second. Okay, and again, this maybe gives you a little insight as to why we chose this particular basis. We chose it because finding this matrix was relatively easy, just based on the geometry that we have. Okay, step 2. Let beta denote the standard ordered basis for R2, and we'd like to calculate the change of basis matrix, taking us from beta coordinates to beta prime coordinates. So we'll take our two beta prime vectors, and we want to write those as linear combinations of the standard ordered basis, which is relatively easy, again, because the standard ordered basis is such a nice basis. All right, and that leads us to a change of coordinate matrix that looks like 1, 3, negative 3, 1. Okay, there's our answer to B. All right, and then finally, we'd like to use Theorem 2.23 to calculate the matrix of t relative to beta, the standard ordered basis, and that's going to lead us naturally to a formula for t. All right, so let's see, the matrix of t relative to beta by Theorem 2.23 is equal to that. Okay, and we've done the calculations that we need above, so Q is 1, negative 3, 3, 1. Okay, T beta prime, you can see from part A, looks like 0, 0, 0, 1. Okay, and then Q inverse, we're going to use that formula for Q inverse. I'm going to just scroll back to it for a minute. Okay, this same formula here that we used in example 5. All right, so you can double check me on this, but we're going to get 1 over AD minus BC. So that's going to be 1 over 1 times 1 minus negative 3 times 3. That's going to be a 1 over 10. Okay, and then that's going to get multiplied by 1, 3, negative 3, 1. Okay, you can look back at the formula and just confirm that I put the numbers in the right place here. All right, and we'll do what we did before. Maybe take this 110 and move it to the front. And then start our multiplication of matrices together, starting by multiplying these two matrices together. That would give us 0, negative 3, 0, 1. Then that's going to get multiplied by the matrix on the far right. And then finally, okay, if we do that multiplication of the last two matrices, you can double check me, we're going to get 9, negative 3, negative 3, 1. Okay, and since beta is the standard ordered basis, we can look at that matrix and write down our formula directly. Okay, so since beta is the standard ordered basis, our formula is t of xy equals, we've got the 1/10 in front here, and we can look at the rows of our matrix to figure out the rest of it. So 9x minus 3y, that's coming from the first row of our matrix, and then negative 3x plus y, that's coming from the second row. Okay, and if we've done everything right, that should be the formula for this projection that we're talking about. Okay, let's do one point check here. All right, and I'm going to go back up to the picture. How about if we choose the very vector that they gave us here, v? You can count the coordinates and see that that point that we're starting at is 6, 3, I believe. Let's see. Yeah, that's 6, 3. Okay, so if we plug that in and use the formula that we just came up with here, we're going to get, let me try to write that a little bit better. We're going to get 1/10 times, okay, and then we're going to plug in x equals 6 and y equals 3, so 9 times 6 minus 3 times 3, that's going to give us 45, I believe. All right, and then into this coordinate, so negative 3 times 6 plus 3, that's going to give us a negative 15. Okay, and if we do the arithmetic, 9 halves and negative 3 halves, or if we like decimals, that's going to be 4.5 and negative 1.5. Okay, what do you think? Does that look plausible? Let's go up to our picture. Where would that point be that we just got out? Okay, so 4.5, that's 1, 2, 3, 4.5. And then, well, I got a short memory here. Negative 1.5, that's going to be 1.5 straight down. And notice, that appears to take us exactly to where t of v should be. All right, so going back down, that looks to be at least plausible based on that one point. And you can feel free to play with this if you want to. Maybe plug in a few more points and see if you buy the result that you're getting.